And thank you so much for joining us here and for checking out this session. So Moonbeam is thrilled again to participate with the Polkadot North America Hackathon. We participated in a bunch of the ones in the past, and the AngelHack team has always done an amazing job. You guys are extremely organized, both in person and virtual, and so we just wanted to say thank you, and we're thrilled to be back and uh, participating in the hackathon. So my session today is targeted and focused on exactly what you need to succeed with the Moonbeam bounties. So we're going to be speaking directly about the items, and hopefully I can give you a leg up on how to build with Moonbeam and the precompiles, and also maybe you'll walk away with an idea of how you want to integrate them into your application. And so just kind of lay out the land. We'll first kind of introduce each of the topics, so the precompiles, and then we'll look at how they work. We'll look at how you can interact with them, and then towards the end, I'll go over our bounties. But yeah, that's kind of what the layout will look like. And as always, if you have questions, there are dedicated channels on the AngelHack Discord for this hackathon. So please do not hesitate to reach out there. You can also reach out to us. Yeah, maybe I can leave my email is kevin@papermoon.com or kevin@papermoon.io. So I also wanted to include that, but the Discord is probably the best place. And yeah, just some background to start off with. I work for Papermoon, and we are a core contributor to Moonbeam. So Moonbeam launched in 2022 in January, and Moonbeam brought Ethereum compatibility to Polkadot. So we're not going to go back through the whole history, but I just wanted to start out with this by saying that Moonbeam's EVM is entirely seamless and entirely compatible with the EVM of Ethereum. So anything you can deploy to Ethereum, you can also deploy to Moonbeam without any changes. But we didn't stop there. It wasn't good enough to just say we're going to mimic the EVM on Polkadot and we're just going to call it a day. Because Polkadot provides you with so many different powerful features typically through substrate palettes. And unless you are familiar with that, you wouldn't be able to access them. And you can't access them from the typical EVM, right? So that's where we needed to bring in precompiles. So precompiles make it possible for you to interact with these powerful substrate features directly from the EVM. And so this is important on two fronts. For one, it makes it so that dApp developers don't need to go out and learn Rust, learn Polkadot, learn Substrate, all of that. Instead, they can just interact with these powerful features of Polkadot through precompiles. And a precompile is just a fancy word for a Solidity interface. That's the way that the dApp developer is going to interact with it, is through a Solidity interface. But of course, under the hood, it's not actually a Solidity smart contract. What it is it's you interact with it through a Solidity interface, but when it gets to a runtime level, it just goes into the particular palettes of Substrate. So there isn't actually a Solidity smart contract that underpins the interface, but rather it's just code for the runtime to say, oh, the user wants to interact with the staking palette, or oh, the user wants to interact with the X tokens palette. And so Moonbeam's got tons of different precompiles relating to governance, relating to staking, relating to XCM, relating to X tokens, and relating to convenience and ease of user experience features such as the batch and the call permit precompiles, which are the focus of this talk and of Moonbeam's bounties. So Moonbeam's bounties are a way for dApp developers and users to access features that would otherwise not be available in the EVM. So if we didn't have precompiles, right, you would still be able to access these features, but you have to go through the Polkadot API. And this means that you couldn't access these features from a dApp. So with Moonbeam precompiles, you can access all of these features either directly from a smart contract or simply from a web dApp. You don't need to have a smart contract in order to access the features of the precompiles. So what I mean by that is we have, if I just go to apps.moonbeam.network, we have a staking dApp here, and this works with the staking precompile. This is a web app, and so it doesn't have a smart contract here, but rather whenever you want to stake, for example, and you press stake here, it's going to submit a transaction to the staking precompile. And so this provides, a very important feature. This is just one example, but there are many others. And importantly, right, this is a web app, right? This is a web app, and you can interact with precompiles either in a manner like this, right, where we're selecting the parameters and we're saying how much we want to stake, and then we're pressing stake. Then the web app here is bundling that up into a transaction, and it'll pop up MetaMask and we'll confirm. But you can also interact with these precompiles via other smart contracts. So as an example here, you could have a delegation DAO. And this is actually one of kind of the contracts that we build in Moon Builders Academy or in other examples that we put on YouTube and stuff like that. But the way that works is it's an autonomous smart contract that allows users to deposit funds. And once the delegation DAO, as it is known, once it amasses enough funds, then it will autonomously go and delegate to a collator. And so we actually see part of this in real life here. I'm below the limit. I have 51 Glimmer, and I actually need 63 in order to meet the staking minimum. So if I built this and launched a DAO, then I might be able to meet the minimum if others join in as well. So that's just a quick example. And yeah, I'm really excited about precompiles, and we're going to talk a lot more about them. So as I was saying, right, it's important partially because users who are coming from Ethereum, or they're coming from BSC, or they're coming from another EVM chain, they don't need to spend a lot of time learning about Polkadot. We want to make Polkadot less intimidating. And so you don't need to go out and learn Rust or Substrate or anything like that. You can think of, they may only know or be familiar with Ethereum, for example, and that's perfectly fine. They don't need to go out and learn, how to interact with the Polkadot API. They don't need to go out to Polkadot.js apps. So we think that's pretty powerful. So what do you need to know? You need to know a couple things. So you need to know what functionality you're looking for. What precompile is it that you want to interact with? And you can find that here on our docs site under builders. And if we go to palettes and precompiles, you'll see Solidity precompiles right here. And so you can see we've got a huge list here. We've got batch, of course, and we've got call permit, which is the focus of this workshop here. But there are many others. And so just to kind of touch on some of the other ones, we've got an identity precompile. We've got a native token ERC20 precompile. So what this is this allows you to interact with Glimmer, which is the token of Moonbeam. You can interact with Glimmer as if it was a wrapped Glimmer token, as if it was W Glimmer or wrapped Glimmer. Typically with Ethereum, right, you either have ETH or you have wrapped ETH, but you don't have both. It's not possible for Ethereum and wrapped Ethereum to exist in a user's wallet. You can only move one or the other. Meaning, if you have 5 ETH, you can convert one of them to a wrapped Ethereum, and then you'll have 4 and 1. But it's not possible to say that I have 5 Ethereum and then also 5 wrapped Ethereum at the same time. But that's actually the way that the native token precompile works. Is that you can just have a balance of 5 Glimmer, and then you can choose to interact with that through the native token ERC20 precompile as if it were wrapped Glimmer. And that's just through the standard ERC20 interface. And so other ones, we've got staking functions, we've got XEM functions, and much more. But when we go to one like the batch precompile, the first thing we have here is we'll have a description, and we'll show you where you can access this precompile. So this is the contract address. For each network here, it's the same address, but this is where you can access it and interact with the function. So you need to know the address of it, and you also need to know what function, of course, that you want to interact with. So we'll go through all these functions, and you'll be an expert at this in no time. So yeah, you need to know the precompile address and, of course, the function that you want to call. So we've talked about how precompiles can enable you to access features that you wouldn't otherwise be able to access. That's a very important reason, and that's one why you might choose to build with a precompile on Moonbeam. But a secondary reason is because precompiles can help you to improve the user experience for your users. And that's something that Moonbeam is intensely focused on because at the end of the day, um, everybody knows that, or many, we believe, many people believe, and most people believe that the future is multi-chain. And so with all of these different cross-chain interactions, both on Polkadot and outside of Polkadot, we want to make it easy for users to do the things that they want to do. And so through part of that, they might be switching chains, they might be bridging funds. Um, and just one example is they might not have the native token in order to pay for gas. And so what you can do to make that experience better is you can allow them to do gasless transactions. Make it so that they don't need to have the native token in their wallet, at least initially. Or perhaps another way that you can improve the user experience for your users is to batch transactions together. And so, of course, one example of this is, let's say you have a DEX, right? And a user needs to first approve uh, an ERC20 token before they can swap it. And then, of course, they need to confirm it in a second transaction. Well, one way that you can very quickly improve the experience for your users is to batch those two transactions together. Make it so that they only have to click confirm once. That's very cool. But that's not the only thing that the batch precompile does. This would also enhance security for your users. Now, how does that enhance security, right? For a couple of reasons. For one, users are accustomed to granting unlimited token approvals. And this is not always a great thing. But many dApps, and in particular, this is, less of an issue now, but it has been, kind of in the past with high gas fees on Ethereum, right? Users may not want to have to constantly have an approval transaction that they need to confirm, right? It's a couple dollars each time, could be more than that. But it's something that maybe they don't want to do each time that they swap an ERC20 token. So instead, they'll grant it an unlimited token approval. And this is dangerous because if there were to be some sort of issue, then the user has already granted an unlimited token allowance to that contract, and then funds could be drained at a later point. So that's scary, right? So instead of that, it makes sense for a user to grant a limited approval, only approve the amount that they want to swap, and then swap that amount, right? But again, we're back at square one, right? We don't want to pay each time we want to do this approval. So where the batch precompile comes in is that you can selectively batch an approval and a swap, and you can do it in a smart way. So there are several different methods of the batch precompile. There are three different ways that you can batch transactions together. So one of those, and this is kind of like the simplest approach, is called batch sum, right? And batch sum just says try to execute every single subcall, and if one fails, no problem, keep going, try to execute the next one, and do as many as you can. So that's kind of the simplest approach. There's not really any logic built in there. It's just try to group up all these transactions, try to execute them all. If something fails, keep going, and that is that. But there's another method that you might wish to use, which is called batch all until failure. And so batch until failure is going to try to execute every single subcall that you provided. Once it hits one that fails, it's going to stop, and later ones are not going to be attempted. But everything that's come before that is going to be okay, right? Those earlier ones are not going to get reverted. We're just going to continue until we have one failure. And finally, we have a batch all, and this is all or nothing. All the subcalls must succeed or everything reverts. So even if you have 10 successful calls and the last one fails, the entire thing is going to fail, and all those earlier 10 ones are not going to, the entire transaction is reverted, so those will have never happened. Just to put this into kind of a an example, I figured that I would kind of put together this graphic showing you some sample executions. So for batch sum, let's say your first contract call is successful, your second one fails, and your third one succeeds. So in this case, it tries to do the first one, the second one fails, but no problem. It's going to keep going. Try the third one. That one succeeds. Okay, great. The batch transaction was successful overall, even though one of these subcalls failed. We also have batch until failure. And so in this example, let's say that the first contract call succeeds, the second one fails. So in this case, it's going to stop and it's not going to attempt to execute the third one. So even if the third contract call was valid and it was going to work, it is not attempted. But important to also note here, in this case, the batch transaction is considered successful. Nothing is reverted. It just stops at the first chronological failure that it meets. And so the first subcall that was successful, that's not reverted, that stays successful, and we just like kind of like a hitting the pause button or the stop button. And in the third case, we have batch all, and this is such that everything must succeed or everything will fail. So in this case, the first contract call is successful. The second one fails. The third one is not attempted, and everything is reverted. So even though the first one is successful, the entire batch transaction reverts, and it reverts in such a manner that if you try to confirm the transaction, it's going to say the typical error. You won't be able to. MetaMask will prompt you and say, "Looks like this transaction will fail. Are you sure you want to continue with it?" And so for the example of a swap on a DEX with an ERC20 token, it would make the most sense to use batch all because it doesn't make sense to try to execute the swap if the approval didn't go through. And likewise, it doesn't make sense to grant the approval in the first place if you know that the swap is going to fail. So this helps keep users safe. And in this case, they are not granting an approval that goes to waste or goes unneeded. And likewise, they're not attempting to make a swap if the approval wasn't successful. So this is a relatively simple way to improve the end user experience for your users and to create a really fluid and seamless experience for them. And as we're going to see in just a second, it's not hard to implement. You don't need to make any smart contract changes. It's quite simple, and I'll show you how to do it in just a second. So each method, we talked about three. We talked about batch all, batch sum until failure, or batch sum. So there are just three methods here of the batch precompile, and they all take the same parameters. And those parameters are an array of addresses in the to field. And so this could be either the address of accounts that are going to receive tokens if you are treating the batch precompile just as a way to send value, which you can do. You can use it just to send the native token. That's perfectly fine. But otherwise, you're probably going to be interacting with contract addresses, in which case in the to field array here, you're going to put the contract addresses that you want to interact with. Now, the batch precompile can hold up to a logical limit of something like 99 subcalls. Most likely, you're not going to get up to that limit, but it's just something to more than likely you would first run into kind of gas limit issues trying to include that all. But there is a large limit, and so you can batch together quite a lot. The second field is value. So if we're sending the native token along to users, we're going to include the amount that we want to include there, and it's going to be included in Way. So Moonbeam has the same units as Ethereum. So 1 Glimmer is equivalent to 1 Ether in terms of units. And so if we want to send 1 Glimmer, we'll need to include 10 to the 18th Way in that field. And it's important to recognize here that even though I said you can include up to 99 subcalls, you do need to specify even if they're all interacting, for example, with the same address, you need to copy and paste that address for each subcall. So that's how the uh, precompile keeps track of the different things that you want to do. Is even if you're interacting with the same contract, or you're interacting, let's say you're sending, one glimmer to 10 different addresses. You're going to include those 10 different addresses, and then for value in the array there, you're going to include one, 10 times. And that goes the same for value, for call data, and for gas limit, with the exception of if you want to leave a field empty. For example, if you're not sending any value, you can just include an open and close bracket. You don't need to specify 0, 0, 0, 0, or anything like that. You can just leave an open and close bracket. So for call data here, this is the call data that you want to specify. So if you're interacting with a smart contract, what is the function that you want to call, and what's the call data that you want to pass to it? So this would be the function selector and the data that's getting submitted to that method. And so we can grab this, and we will grab this from MetaMask. If you just copy the, let's see, you can't see MetaMask right now. That's good. You're just going to copy the raw transaction data if you go to the hex tab in MetaMask. Okay, and lastly, gas limit. This is optional. You don't need to include it, and we won't include it in our demo. But if you wanted to specify a gas limit for each subcall, you can. And you can section off, you can segment the batch call by different amounts of gas. You can give some more and some less, or you can just leave it with an open and close bracket. That is perfectly fine. And in that case, there is no limit. It will take as much as it needs according to typical gas estimation amounts. Okay, so let's do a quick demo of batch.sol. So the first thing that we do, in any case, I'm going to reset my IDE here so that we're all on the same page. Let's see. So I'm going to delete batch.sol. ERC20, we can leave that here. Actually, let's delete that too. Okay, so where do we go to get batch.sol, right? Your first stop might be the Moonbeam doc site, and this is going to have everything you need. So the two important pieces that we need here are the address of the precompile, and we also need to get the interface itself. And so we can open up batch.sol, and we can see everything here. Now, one important note here is that if you didn't get the contract address from the Moonbeam docs, you can also get it here, either as a comment or as a variable here. So you want to copy the entire contents of this and paste it into Remix. So let's create a new batch.sol. And let's compile it. It compiles. And make sure that on the deploy and run tab, make sure that you're connected to injected provider MetaMask, and make sure that your MetaMask or your wallet of choice is connected to Moonbase Alpha. If you're not sure if it is or not, on the Moonbeam doc site, we have this big connect wallet button. Just press that, and it will connect you to the appropriate network. So Moonbeam, Moonriver, or Moonbase Alpha. And if you choose it, then it will prompt you to either switch networks if you already have it, or it'll give you the RPC information and everything like that. So you don't need to go and add it manually. Now, these are precompiles, so we're not deploying anything. Don't click deploy. Instead, we're just accessing the contract that's already available. It's already available to us. And in my example, I will go and demonstrate batch all. And let's first start. You can see I have, I should have a decent balance. I have something like 1,300 dev tokens. Let's start by just sending some tokens to, let's say, 3 different or 2 different users. So I need to start with an open brackets, and I also need to include quotes for the address. So this is very important. If you don't include quotes here, open and close, then you will get an error. So I'm going to paste in my second address here, and I'm going to include a close bracket. And we're going to send one Glimmer or one dev token to each account. And remember, we have the way to Gwei conversion here. So if I do way to Gwei, we'll go ahead and do just one to both. So for this value field, you don't need to include quotes. And we have 18 decimal points here corresponding to one glimmer or one dev. For call data, this is where we'll put the contract call data. We'll do another demo where we have that, but we don't have any call data here. We're just sending funds in this first example. So we're going to have an open and a close bracket, and we'll leave it at that. For gas limit here, we could specify a gas limit, but we have no need to. So we're just going to have an open and a close bracket. Remember, for each of these, I have 2 subcalls in total. So I have two addresses and I have 2 values. Even though these values are the same, you need to duplicate them. Otherwise, the precompile won't know the value for each. Cool. And once everything looks good, press transact. And I just have a MetaMask pop up here asking me to confirm the transaction, which I'm doing. And we'll return to it in just a second. In our next example, just to preface what we're going to do, we're going to interact with a simple incrementer contract. Okay, and our transaction was just confirmed. So let's open that up on the Blockchain Explorer and see what it looks like. Cool. So if we expand, let's see, I think it can refresh and I think it will delineate it out. Let's see if I can expand. So it's batch all and it's transferring funds, but I thought it would split it out into what's been transferred. Let me check a prior transaction and see if it shows there. So if I check a prior one here, it's still, I think it might just take a minute for this to get indexed properly. But in this prior example here, we're transferring one dev and one dev to each of these addresses. And so I think it just takes a second to index that properly. Yeah, so this is the transaction that we just did 1 minute ago, and it's transferring one dev. It looks like it's coming from the batch precompile, and it's going to each of these addresses that I specified. Cool. So that was an example of using batch all in order to send funds from one account to the other. But more than likely, if you're using the batch precompile, you're probably going to be using it to do contract interactions. So let's take a quick look at what that would look like. And to do so, I have this extremely simple incrementer contract. All it does is it has one function, which allows you to run up a number. And so if we check out the number, it's currently at 271. It's also got a timestamp function here, but we're interested in this number one. And so what I'd like to do is I'd like to, multiple times, I'd like to call the increment function using the batch precompile. So what I will do is I will go ahead and get the address of incrementer here. And I'm going to paste that into our to function here, remembering to use quotes. And let's say I want to include it, let's say 3 times. Oops. I'm going to making sure that I include open and close quotes for each time. And a close bracket at the end. So that looks good. For the value section, we're not sending any value to the contract, so we're just going to have open and closed bracket here. And in terms of the contract call data, so you can get that by simulating a transaction. If we're going to press right, we have the data here. We can also get it by pressing right and then going over to the hex tab in MetaMask and pressing copy raw transaction data. Now, because this function doesn't take any parameters, the function selector here is the same as there's no additional call data here. So we can copy it straight from here as well. But in this case, I'll copy it from MetaMask just because I think it's easier to copy. And so that call data looks like this. Remember, we're going to put it in quotes again. And I have 3 different contract calls of increments, so I need to include it 3 times. Remember, if you're having any sort of errors doing this, the most likely case is, the most likely problem is really the simplest one. It's just that you probably forgot a quotes, or you forgot a comma, or you forgot a closing bracket, or anything of that sort. And so what I would recommend is simplify, right? If you're doing 10 different things, scale it down to 1, make sure that that works, and then amp it up to 2 or 3 or more. But usually when you're getting an error like this, it's usually a formatting error. So for our gas limit here, we don't need to include a gas limit, so we'll leave that blank. And let's do one last check here on the contract and see what the number is. It's 271. If everything works, if we did this properly, it should go up to 274 because we're calling it 3 times. So the first transaction here that I'm getting in MetaMask was just from the prior one when I was copying the call data. So everything looks good, and I'm going to press confirm. And this should go through in just a second or 2. Cool. And it was confirmed. Let's go ahead and go back to incrementer.sol on Moonbase Moonscan. If we refresh the page and we check, we see that that number is now at 274. Okay, cool. So this was batch all, right? We also have batch sum, and we have batch sum until failure. So they each take the exact same parameters. There's no difference between any of these functions in terms of the parameters that they take. Cool. So let's head back to the slides here. And let's move on to gasless transactions. So we looked at the batch precompile. Now we're going to be looking at call permit. And call permit .sol is the precompile that enables gasless transactions to work on Moonbeam. And we'll talk a little bit about how that works. And call permit.sol is quite well designed and quite cool because it does not require any smart contract changes. You may have heard of types of early gasless transactions on Ethereum where they require some changes to smart contracts or anything like that. With call permit, you can keep your contract exactly the same. All you need to do is perhaps make a change to your web dApp or to the front end of your dApp in terms of how a user is interacting with it, and giving them the option of doing a gasless transaction rather than prompting them with a transaction. You're going to prompt them with a signature request. And with this signature request, of course, it does not take any gas. And then you will grab that signature, and then at a time of your choosing, and according to the deadline that the user signs, you will either submit that right away, or perhaps you will hold on to it and submit it at a later point if the deadline that the user signed is not already passed. So let's talk about this message, and let's talk about what the user's signing, right? So the user is going to sign a message, and the message is constructed following this EIP 712 standard, which you can read more about here. But essentially, it's a specification and a way to approve a transaction that can't be just copied and captured. And so if you sign it once, I can't go take that. Let's say you sign a transaction to give me 1 ETH, right? We need to make it so that if you sign that transaction, that it can be, doesn't have to be executed, but it can be executed only once, right? And if I were to just try to take that and submit it 10 times and try to send myself 10 ETH, that would fail. So I could only send myself 1 as according to what you have approved. And the way that this is done is through the signing of this structured type data, which does include a variety of different pieces, including a salt and a domain separator, and all that, so that it is only so that it is unique, right? So um, you're going to sign that, and not only is it unique, but it's also presented in a way that's readable. So very early on, actually, let me see if I can pull this back up. Very early on in EIP 712, this is what the signature looked like. It looked like this message, a big, long message. Or sorry, very early on in Ethereum, this is before EIP 712, you had to sign a message that looked like this. And so this could either be, you know, doing exactly what it says. If it's sending 1 ETH, it might be sending 1 ETH, but it also might be draining your entire wallet. It's impossible. It's just nearly impossible for the user to tell. And so EIP 712 also made it so that you can actually read what's going on and read what you're signing. So you can see more clearly, okay, we're sending from here to here. We're sending the contents of this message. It's including this amount of ETH or not. And so it's very important that the user knows what they're signing. Cool. So as a dApp developer, you're going to present to the user, right, this signature or this message and ask them to sign, in which case that will produce a signature. And then you're going to take that and you'll submit that signature through the precompile. So the precompile has a variety of different fields here for you to use. So if we go over to call permit, it includes a dispatch method, and the dispatch method includes all the different parameters that you're going to have. Who's it coming from, meaning who is the signer, not who is the dispatcher, but who is the signer of the message. Who's it going to? How much value are they sending, if any? What's the call data that's being included? What is the gas limit? This is important for security purposes. You need to provide a gas limit, and you also need to make sure that the message that was signed matches the amount that you're submitting to the precompile. So if the user authorizes, 1 million gas, and you try to submit it to the precompile with 2 million gas, it's going to fail because the signature is going to change in that case. We also have a deadline, which is in Unix seconds. And so this is the time period by which the message needs to be dispatched. Otherwise, it's not going to be valid. Okay, and then we also have the different bits of the signature, the V, R, and S values, which constitute the signature from the user. And so the person that's going to submit the signed message to the call permit precompile, this could be anybody, right? It could be you as the dApp developer. It could be a third party. It could be a, you could use a third party to do this. That's perfectly fine. But it might just be built, into the front end logic of your dApp. You might have, an account that you funded with some Glimmer, and you might just be the one, dispatching these transactions. So when you, as the dApp developer, when you're taking this signature from the user and when you're submitting it, there are going to be some checks, right? So when you're submitting all these values, right, the precompile is going to verify that the signature is valid. It's not going to allow you, or you're going to get a message that says, this transaction will revert. In the event that the signature is invalid or any of these bits are not exactly right. So let's think a little bit about the flow within a dApp and kind of compare it to the normal flow for a normal transaction, right? So it is very similar, except rather than presenting the user with a transaction pop-up saying, hey, please confirm this and pay for it, instead, you're going to serve them with a message that you'd like them to sign. And now's a great time to mention that you may have interacted with smart contracts in the past that have asked you to sign messages specifically for token approvals, right? And so this is a standard that's been around on Ethereum for a while, but it's relevant and pertinent to token approvals only, right? ERC20s, that type of thing. It's important to keep in mind here that the call permit precompile allows you to dispatch any arbitrary transaction. So users can sign a message to do anything. This is really cool. This is really powerful. So this also means that you can do things like you can build dApps where um, you might have things that you need to enforce on chain at a later point in time. You might allow people to do like a limit order or like a different type of transaction that doesn't need to be executed right away, right? You might just need to like have a guarantee of some sort, maybe like a deposit of some sort or a limit order on a DEX. All of these are things that could take place on chain at a later point in time, or perhaps like a cancellation or something gets voided. You can do all that, and it is quite cool that you can do all of this. Um, and you don't need to have it be an on-chain transaction right away. You can have it, of course, be an on-chain transaction right away. You don't need to include like a gap or a time limit or anything like that. But you can simply take the signature and you can go ahead and submit it to the call permit precompile right away. Um, and of course, you are going to want to check that the uh, call that you submitted to the precompile that was successful. So once that's successful, then you know that the user's transaction that they signed, the one that corresponds to the message that they signed, you know that it was successful. And so you're going to want to update your dApp front end if you have any logic that needs to come up later, or a confirmation, or if you need to change the state of your site. That is kind of the time that you want to do it. So again, the logic here very similar to a typical smart contract interaction. Rather than presenting the user with a transaction pop-up, you're presenting them with a message pop-up. And then at a later point in time, or at that same point in time, you'll then submit that through the call permit .sol. I think we've already talked typically about everything here, but just to reiterate, we're signing a message in the style of EIP 712. So this means that when they're signing it in their wallet, they're going to be able to see the details of what they're signing. So it's not going to look like that crazy long string up here. Instead, it look like a logical data that they're seeing exactly what's going on. And these are all the parameters here on the right. And another thing here is that, yeah, you don't need to change your smart contracts. You don't need to adapt or redeploy your smart contracts or anything like that. This works with any arbitrary contract and any arbitrary interaction, which is really, really cool. It would be tough if you had to rewrite all of your smart contracts. Okay, so I wanted to give an example of this in action, and we're going to use the same incrementer contract that we did before. So let's make a note of the current value, which is, what is it, 274? That's exactly where we left it. And we're going to use the call permit precompile to sign a message and then dispatch it from another account. So what we always do is we're always going to go and grab the interface of call permit.sol. So go ahead and copy it, and we'll paste it into Remix. We'll create a new call permit.sol. And let's go ahead and compile it. And let's head over to the deploy and run tab. Everything else has stayed the same, except we need to change the address to the call permit address. And we'll press add address. And let me just minimize here the batch one. Let's open up call permit. And we can see dispatch here. That's what we're going to be interacting with, is dispatch. So we've got a bunch of values here. Let's use this demo dApp here in order to sign a message and construct what we'd like to, oh, sorry about that. To sign a message and construct what we'd like to construct. Cool. So this is just a quick demo dApp, and it's going to allow us to specify the values that we'd like to provide, and then we'll get a corresponding signature accordingly. So we were going to use the incrementer.sol. So let's use that as our to. The value, we don't need to provide anything, so we can leave that blank. The data, we need to get the same data that we had here before when we were writing. So it doesn't take any parameters. So we're going to use that same call data here. And I'm just connecting to MetaMask here, so it's easier to copy the contract call data here. And we'll come back here and we'll paste this in for data. For gas limit, the gas limit, you do need to specify a value here. So let's specify a million gas. This is going to be, way higher than we need here, but it's just it's unnecessarily large. But I also don't want to go through and provide too low an estimate. So let's go ahead and also look up the current Unix timestamp. So this is right now. If we try to submit this, it will fail, but we can just tweak it a little bit. We can add an extra year, so we know that it's not going to expire. So we'll put this in as the deadline, and when I press sign, I'm going to get a pop-up in MetaMask here that asks me to sign this data. Now everything that is here, essentially, it's asking me to sign this exact same data. So it's giving me the from account, the to address, which is the same one here. It's giving me a value of 0. It's giving me a data of this, a gas limit of 1 million, and a deadline. It's also giving me a nonce. And this nonce is something that you can find. This is a global nonce. It's different from your nonce in terms of how many transactions you've submitted, but I'll go and show you where you can find that data. So we're going to press sign, and we'll get the signature. So now if you're watching this and I haven't submitted this yet, you could go and take this and copy all of this, and you could go and submit the transaction on my behalf based on what we have here. So before I do that, let me just show you the nonce information. So I'm going to copy the account. If I were to go into Remix and look up global nonces, we'll see here we have 5. So there have been 5 transactions here that have been submitted on behalf of this user. So that's my account. I'm going to make sure to change the accounts that I'm connected to so you know that it's not coming from the first one. So I'm going to change it to this third one here. And I'm going to need to take all of this data here and plug it in exactly as you see it. So let's do that. Let's get the from account. Again, the from account, this is who signed the message. This is not who's going to be dispatching it. This is who signed the message. Let's get the to address. The value is going to be 0. The data is the call data for the increment function. The gas limit we said was 1 million, so we can plug that in. A deadline. Again, don't tweak any of these numbers. Even if the value is similar, if you put a deadline that's not the exact same, it's going to fail. The values have to match exactly. And pay particular attention here to the V, R, and S values. So these are ordered here exactly the same as V, R, and S, but in some cases the ordering might be different. So just make sure that you're copying them in the right place. If you mix up the values here, the transaction will not go through. Okay. So I've got everything. And notice how the nonce value here, that's not something that we needed to specify manually, but it's something that's signed. And so the demo dApp here just goes ahead and gets that data on its own. It makes a query and then it presents that in the message. So we signed a message that included the nonce of 5. And this is what prevents this transaction from being submitted multiple times. If we were to dispatch it once and then try to dispatch it again, it would not go through because that nonce has since changed. So everything looks good here. Remember that our value here was 274, and we are going to check the results of that, and we'll expect this to go up to 275. So let's press transact, and when we press transact, we are going to confirm a transaction. So the dispatcher account needs to have some funds. It needs to have some dev or some glimmer, and anyone can do it. Anybody who has the signature can submit this transaction. All right, let's go ahead and do it. So MetaMask just popped up and asked me to confirm a transaction from account 2, which is this account right here. Cool, and it was confirmed. Let's go ahead and open up the transaction and see what it looks like. So I need to go over to account 2, and I see the dispatch call. So we can see we called the dispatch function on the call permit precompile. Cool. We can also see all the data here, including the signature values and everything like that. So that looks good. Our gas limit was extremely high. We only needed a little bit. But let's go ahead and check the incrementer contract. Let's refresh it. And if it went through, we should see 275. Cool. So we see exactly what we were expecting. You can absolutely, this is a public website called permit, callpermit-demo.netlify.app. You are more than welcome to use this site. Hey, Lamont. Oh, so glad to see you here. Oh, thanks. Thanks, Lamont. I appreciate that. Great to see you here. So we also wanted to mention that, yeah, you can use this app. You can also use, you might write your own JavaScript in order to create the signature. That's fine too. We have examples of this on the Moonbeam doc site. And, there are plenty of, open source examples that you can find if you do some Googling on how you can get these signature values. So that won't be, the hard part. That shouldn't be the hard part. Cool. So let's go back to the slides, and I'm just about wrapping up. And I want to give you a quick real world example, right? So if we go to swap for gas here, this is a feature that StellaSwap has. There's also a similar feature on BeamSwap and SolarBeam and other Moonbeam dexes. And what this allows you to do is, let's say you've just bridged over to Moonbeam. Let's say you've bridged over, 500 USDC, but you don't have any Glimmer yet. So some bridges might give you like an airdrop or something like that. But if you've got just, USDC, or you've got just XC dot, for example, you can swap some of these tokens. In this case, StellaSwap supports several different ones. But you can do a gasless swap in order to get some Glimmer tokens for gas. So if I wanted to make a swap, I just fill this in. I'll connect a wallet. It'll prompt me to make a signature, and it will give me some Glimmer in return for exchanging some of the other token that I have. And so all you need to do here is sign a message, and StellaSwap will go and submit this transaction, which is very cool. And make a note, usually for the swap for gas feature, usually dexes will take a slightly larger fee for the convenience capabilities of this, of giving you the ability to swap in a gasless manner. Cool. And so this is just a screenshot here. This is actually from SolarBeam. And when you are going through and trying to do this gasless swap, it's going to give you the message data here that you're signing, and you'll sign it and approve it, and then it'll go ahead and make that swap. Here's a link again to the demo that we've done. And I wanted to wrap up by just going through our bounties. And our bounties here, if you aren't already familiar with them, we have 2. And the first one is to create a gasless transaction experience with Moonbeam. So use the call permit precompile, integrate it into an existing dApp, or build a dApp that uses it. And we have a $3,000 first place prize and a $2,000 second place prize. Now, in both of these examples, right, we want to be as flexible as possible. We want you to be able to stack bounties wherever you can. And we're also making it such that you don't need to be the original creator of the dApp. So if there's an it needs to be open source. You need to do this all by the book. Um, if you have if there's an open source dApp that you built maybe in a prior hackathon, or there's an open source dApp that's just out there and you want to improve it, you can do that. Now, of course, you're going to be judged only on what you improve. You're not going to be judged on the existing UI or the existing features of a dApp. But we want to allow you to, improve existing stuff that's already out there, and we'll judge you on that. So, same thing goes for batch.sol. Use the batch precompile to batch transactions together. You should, do it in a logical manner, right? If you're doing the approvals, you should do batch all based on the design of your dApp and what you want to do. Um, hopefully you're giving some thought to which method you want to use, and using it in a logical manner. So for both of these, we have the same prizes. So $3,000 first place prize, $2,000 second place prize. We've got 4 prizes in total. And just a judging note: um, the requirements, right, of both these bounties. For the gasless one, you need to use the call permit precompile, and you need to have some smart contract code deployed to Moonbeam or Moonbase Alpha. And same thing for batch.sol. You need to have an action with the batch precompile, and you need to have some smart contract code deployed to Moonbeam or Moonbase Alpha. Um, yeah, that's those are our bounties, and we're very excited to see what you built. So I'm going to be around. I'm around in Discord. You can also reach out to me at kevin@papermoon.io. And we also do devs open mics on the Moonbeam Discord. We do that every Thursday at 1 p.m. Eastern. So 10 a.m. Pacific, 1 p.m. Eastern. And that's also 5 p.m. UTC. So I want to wish everybody good luck. Thank you for stopping by. And yeah, good luck. We can't wait to see what you built. And hopefully, I'll see some of you in Austin as well in just about 1 month.
All right.
So thank you so much.
Thank you. Thanks, Kevin.
Thanks, Gladys.
Will be joining us at Polkadot Social, which is an in-person event where our grand finals would be happening. And yeah, thanks so much for also going through the bounties from Moonbeam. There are 2 challenges, so really exciting. And yeah, I think with that, we can end the workshop, and we'll share it on our participants guide if anyone wants to check it out. Okay, thanks.
Thank you so much.